Mic issues? Okay. Whoa, there. Did I finally get it? Back row, can you hear my mic now? Huzzah. Whew. Someday engineers will solve the microphone problem. Probably the same time they build a copier that never jams. We're waiting. Okay, great. Let's talk about this. So, you know what, for funsies, I haven't looked at the poll everywheres. Let's see where we land on the poll everywheres. So there was a few steps to get there. Let's see. Oh, okay. Shout out to this person. We're going to hit present. There we go. Okay, that looks more appropriate. Okay. Oh, I see. I see how we're playing this game. Me too. I get it. I get it. Okay, well, let's walk through it and see how these things shift as we go. Get it, get it, get it. Okay, so, okay. Now, remember the way that I like to do these things is I like to do the stuff that hopefully is the least scary and work my way to the most scary. So I want to start with the base case. Does anyone, brave soul, want to raise their hand and tell us how they maybe would code model the base case? What model did you get for that will be at the top of that recurrence? Maybe you can even just give me the big O. Don't have to have a number. Yeah. O of 1. Yeah. So if we kind of look at this base case, you know, here I'm just doing my some printlns, some comparisons. We get a base case. Maybe it's +2. Whatever. Something in the O of 1 category. That's all I really care about. Because remember when we're doing master theorem, whatever's in the base case ends up being letter D. And see how letter D doesn't impact? And that makes sense, right? Because the base case is really only going to happen one time when you run your code. So it's probably not going to dictate a lot of the code growth function. So that's why the base case, we almost kind of don't care that much about it. Kind of gets thrown away. But it finds its way in the recurrence. So it gets a shout out, though it doesn't have a lot of influence. Okay. Now let's talk about the recursive case. So we have a for loop that runs 16 times, and then inside the for loop is a recursive call to myself. That's what a recursive call is, where we go n over 4. So in the recurrence, what am I going to put between the parentheses of the recursive function call? I'm going to have f of n as a factor of itself. What am I going to put between the parentheses? How does n change from one recursive call to the next? Yeah. N over 4. Yes. Plug and chug. It's in here. We just lift it up. Great. How many recursive calls are we going to make? What is the coefficient to the recursive call in the recurrence? 16. Absolutely. So there we go. Here's the recurrence. So this recurrence is the code model. And since Casey was nice and gave you a piece of code with this particular format, we get to use master theorem. So now we need to find A, B, and C. Can any brave soul tell me what is the value of A for our recurrence? Yes, right here. 16. It's the coefficient. Okay, what is the B? Who wants to tell me what the B is? Oh, I see it. Yeah, we've got some of these. 4. Exactly. We just pulled it right out of there. Okay, now this one is a little trickier. What is the value of C in this case? Oh, okay, I see a lot of this happening. You're correct, because our work outside of the recursive call, the non-recursive work that happens within the recursive case, is like this singular println. So it's a constant amount of work. There's no factors of n. So according to our little definition here, f of n is literally just +1. So the exponent of n is 0 because there's no factors of n in the non-recursive work within the recursive branch. Questions on how we got A, B, and C? Yes, please.
So 1 could also be 1 to the first power, and could C be equal to 1 in that case?
Sorry, say that one more time.
So 1 to the 0 is 1.
1 to the 0 is 1.
1 to the 1 is also 1.
1 to the 1 is also 1, yes.
So could C be equal to 0 and 1?
So the reason that C is equal to 0 is because we only care about terms of n. And if you go back to the slides from Wednesday and read that thick slide where I was like, why master theorem works, a lot of it is we are paying attention to how n influences the growth rate of our function. So in this case, because there's no term of n, there's no influence from n in the recursive case, so it's a 0. So I don't really care what the exponent of 1 is. I don't care if it's a plus 1 or a plus 1,000 off there. It's independent of n, and thus C is 0. Cool. Now we have A, B, and C. So we plug it into our little system down here. And I'm not going to lie, I have no idea how to do that math without a graphing calculator or Wolfram Alpha or whatever. Maybe you all have a more modern system to find the answer. Maybe Google just does it for you. I don't know. But apparently, log base 4 of 16 is 2. I'm sure that makes algebra sense. I believe it. And since 2 is greater than 0, we end up in this case, and then we plug again, and we end up with theta of the n squared. Huzzah! So shout out to those folks. Let's see. Did we continue to change our opinion over here? Wow. Okay, there you go. So shout out to the current 75%. Yeah, sure, change your answer. It's fine. Guess what? I never look at the answers. I have absolutely no idea if you've been getting these answers correct or not. I just look at if you answered. So there you go. Shout out to the 145 of you at least that are probably sitting in this room right now. Okay, Casey, reactivated. Great. I remember how to do these things now. Okay. So that concludes the analysis portion of this course. You now have everything you need in order to answer all of the analysis questions on exercise 2. I know at the beginning of the course, we did like that fun design stuff. Remember we were talking about playlists and like printer jobs and things like that. And I was like, oh, this class has no right or wrong answer as long as you can justify it. It's about design. And then I immediately pivoted into all this math stuff. Like I just bait and switched y'all. We're going back, I promise. From here on out now, it is all about what tools can we add to your toolbox and what creative ways can we recombine those tools to invent amazing things. But now, if you're not too traumatized, you have wonderful skills to analyze the possible different designs. And from here on out, I'm going to show you more and more complex scenarios so you can apply your analysis and decide which design works best for you. That was the whole point of what we just accomplished. Great. Okay, thanks. All right. I think I'm so fancy with the animations, whatever. Okay. A couple announcements. Reminder, Project 1 technically was due yesterday, but the late turn-in closes on Sunday. Exercise 2 will be due on Tuesday. We're going to go over some more stuff today that will help you answer the hashing questions. Also, the best worst case scenario is always confusing. If you're confused by best or worst case scenario, you're not alone. It's probably the most confusing thing about this course. And shout out to our wonderful TAs who I'm sure did their best to try and clarify it in section, but extra shout out to Yafka who wrote a really nice, clear explanation of best versus worst case, and it's now pinned on the ed board. Go read it. If you have further questions, we will answer them. You are not alone. And since you're not alone, it's mostly on us as to why that's confusing. So we're continually trying to make that as clear as possible. Project 2 was released yesterday. Now, it is due in 2 weeks. I, too, was a student once, and my brain would have heard that and been like, sweet, I'm not going to do any coding for a whole week. But I didn't give you 2 weeks because it's secretly a 1-week assignment and you get a break. I'm obviously not that kind of professor. I gave you 2 weeks because it is a 2-week assignment. And every quarter I say this, and I say, guess what? I know next week office hours are going to be real suspiciously quiet. And then every year, me and the TAs have to put extra office hours the week following when you all procrastinate, because we're human. And then things explode that week. And now here is the real problem. Because we have 3 holidays on a Monday this particular session, the week that Project 2 is due also happens to be midterm week. So please start early on project 2 for me, for you, for all of our sakes, for our sanity, okay? I know I would have ignored myself if I was in your shoes, so don't be like me. Be the best version of yourself and start early on project 2. The other thing I will say is there are 2 things you're going to implement in project 2, and since they are 2-person projects, I know y'all are gonna rochambeau for who does what. And then the day before it's due, you're gonna come into office hours and you're gonna be like, it doesn't work. And I'm gonna be like, what's this line of code doing? And then y'all are gonna be like, I don't know, my partner wrote that line. And I'm like, oh. It's an incredible project to pair program on. If you haven't found a partner yet, I strongly encourage you to find a partner. Now's the time. It is a significant step up in complexity yet again. But it doesn't kind of continue. It's just something about P2 terrifies students, and I don't fully understand why. We keep trying to make it cleaner and cleaner, I promise. This is also me trying to terrify you just a little bit into getting started early. And then a reminder that 2 weeks from today, here in class, is our midterm. It is an in-person exam. Then we take it, we grade it, we give it back to you, and then you get about a week of digital time to change your answers and resubmit for half of the points you missed back. This is also me saying, if you have any particular planned academic reason that you cannot physically be here 2 weeks from today, please send me an email now. It's a very different email conversation if you send it to me now versus 2 hours after the exam has started. Any questions? Yes?
Would you say that P2 will take longer to complete than, let's say, P1?
Yes. P1 is a 1-week assignment, and P2 is a 2-week assignment, and I would say it definitely takes at least twice as long as P1. So I gave you twice as long. At least that was my thinking. Any other questions? Casey, can we use notes on the exam? Yes, you can use notes on the exam, but because, like the internet and ChatGPT, they all have to be on paper. You can't have anything electronic with you in the room, but if you want to print out all the slides or print out some textbook and flip through all of those things, that's your business, not mine. Behind the scenes secret, whenever teachers tell you that it's unlimited notes, it's a trick, because you're going to waste more time flipping through your notes and actually do more poorly. So I actually encourage you to make one of those nice, quick reference notes guides. It turns out that even in the act of making it, you learn so much, you rarely use it. But when people think they have unlimited notes and they don't make the summary sheet, they have to look through things and they waste time and they do much more poorly on the exam. But you're an adult. It's up to you. So prepare your notes as is appropriate, but remember, 2 weeks from today, here, be there, be square. Yes?
Will there be a study guide or a list of concepts for the midterm?
Yes. A week from today, I will tell you exactly what's going to be on the exam. Our wonderful assessments team will have all of the past exams for you to study from and some makeup things, and we'll talk about it in a bunch of details, but I can tell you right now that the exam will cover all materials through the end of week 4. Okay, great. Let's learn some new stuff. Okay, so we are now, like I said, leaving the analysis portion. You don't get to forget it, unfortunately. You now just get to apply it to everything for the rest of this class. But now we're going to start to pick up new data structures. And I wanted to talk about an ADT that we as engineers are just particularly obsessed with. It's called the map. I'm going to refer to it as a dictionary. And all I really just mean is a data structure that follows the ADT implementation where every singular entry of data actually has 2 pieces, a lookup value or key, and then the value associated with it, we call that a value. If it helps in your brain, you can think of this as the word and then the definition, or maybe like the person's name and then their number, something like that. So you have a value you're trying to search for, and then a value associated with it, so you have these pairs of data. They tend to be the most common ADTs that we use because think about it as sort of a density of data situation. You may have used hash map and tree map in the intro series. Hash map is something Java built for you. And guess what? P2, you build it. Yay! So all of today, we're going to talk about how to build that thing called a hash map. Here's another review. Technically, by definition, maps do not have an order. Maps are about optimizing for finding a key in a collection of data. It's all about lookup. It's all about reference. So put, get, contains key, remove, and size are our classic methods here. One thing to call out is you can notice that get is based on the key. You give it the key, you get the value back. Put adds a new entry, but keys must be unique. So if you call put and you're using a key that already exists in the dictionary, you will overwrite whatever is already in there. Keys must be unique, because that sort of like breaks the lookup property otherwise. So a map is a collection of unique keys and their associated values, and we're probably going to spend the next 4 structures figuring out the best way to structure this. Okay, so we could implement a dictionary with an array where we have each index of the array containing these pairs. So in this particular context, the key is the A and the value is 1. The key is the B, the value is the 2. Now, if I wanted to find something in the array, again, it's unordered. I'm just sort of using indices of the array as places to store stuff. So in order to find anything, I would have to do a linear search. So I get linear runtime across all of these things. Now, again, best case, worst case scenario. Worst case scenario, the thing doesn't exist in that collection. I got to look at everything to determine it doesn't exist in the collection, linear. Best case scenario is the first thing I look at. So our range is somewhere between constant linear, but we don't really care about the best case because we're pessimists. So this is a linear runtime if we just use an array to implement a dictionary. Oh, okay, great. There you go. I added some animations. You can click them yourself. Great. Okay, what if we implemented a dictionary with a linked list? Again, it's nice because it's, a linear structure, but again, I don't care about the order of map. It's about lookup. So we can have a node that each contains a key and a value, but I don't know where it is in relation to each other. So my worst case scenario is still linear. My best case scenario is still constant. So it sort of seems like these two underlying structures, which is what we were using back in week 2, not super well optimized for this lookup scenario. I don't care about order, so why would I use things that are really optimized for a linear order structure? Can we do better? Okay, this is a question that we're going to ask ourselves a ton throughout this course. And a lot of times when computer scientists are trying to explain how we can do better, we think, well, instead of just trying to solve for the perfect lookup, what's a more specific scenario? How can we narrow the requirements and then build something optimized for that scenario? So what if we simplified the problem and we said, okay, well, what if we're just trying to build a lookup where the only type of key is an int? Maybe it's easier to just handle lookups of numbers. Well, what if I then said, I know an array comes with access of an int. We call them the indices. So what if we just built a map where the keys are the indices of the array? That would be pretty cool. So in this context, my lookup value is 3. I put it at index 3. So when I want to get the value stored, I get that constant time, because I can constant time jump into the middle of the array. I've just associated the key with that particular index of the array. Convenient, right? So I'm starting to make the array work for me. So here is some code in order to enable this to happen, where we've got put. We just use the key in place of the index of the array we're accessing. And then we just have all this really nice stuff. And then here we are. What a beautiful runtime. It's like fresh snow before anyone's ever stepped in it. This is the best we're going to get, right? Ooh, I already see hands. Love it. Yes, please, question. Wouldn't this be such a waste of space? Yes, indeed. In fact, I agree. That's probably like the first wasted space. Like, what if we had key values that were 0, and I don't even know how to say this number aloud? Then in order to make our direct access map work, I would need an array that has all of those spaces available to get to the 9999 index, and all of that space in the middle is going to be a total waste. Silly. Also, it only works for integer keys, and dictionary kind of by definition isn't integer keys. But we get that fresh-driven snow, perfect constant runtime. So now we have sort of this idea where we're going to associate where something is in the array with the index of the array, but we're going to continually iterate on how we can add clever ways to get from what we want to store to a specific index of the array without, in this case, wasting space, like our friend suggested. So first of all, can we do this for, say, any int, even though we don't want a massive array? So we could do that like giant array, where we just have everything mapped directly to that index, but we get super wasteful stuff. So here comes this delightfully powerful and, in fact, one of the most important contexts in computer science and, frankly, the way the world works today, this following idea. What if instead we create a smaller array and we add a translation step from the int we want to store to the int of the index of the array where it is stored? So we had just this little translation to go from one number to a different number. This is called hashing. In fact, that is technically the definition of hashing. It is just a way to formulaically or algorithmically take one number and transform it into another number within a specified range. Now, I'm going to talk about hashing in the context of these data structures, but you all use hashing all day, every day. It's how we keep data safe. It's how we protect passwords. This is essentially like the secret codes behind how we send information back and forth on the internet. Hashing. It just means take your data, turn it into one number, add a secret translation step that then tells me where to put it in my data structure. And in fact, there are massive research labs all about how to do this translation step as effectively as possible. So the way we're going to do it here is, remember in my direct access map code, it was like I was just using the key straight up in between the square brackets of the array. I was just using that directly. Now I'm going to add a very special method called the hash function that's going to take in the number that I want to hash, or the key value I'm trying to find a place for in my array. It's going to do some magical translation. Then I'm going to fit it within the range of the indices of the array that are available and spit it back out. That's the role that the hash function is going to play. So hashing technically is just taking one number and transforming it into another number through some sort of deterministic process. But then we need to make sure that that number fits within the range of elements in the array that I have available to me. And so this is just a reminder of that mod operator, that remainder operator. It's our best friend in hashing because that's how we're going to limit numbers to a specified range, i.e. how we're going to limit numbers to the eligible indices of the array in which we can store it. And here's a bunch of review, and you can go look at, I actually really like this Khan Academy lesson on it, so you can go watch that if mod is unfamiliar to you. Okay, great. So let's see how this works. Here is an array. I want to put the dictionary entry with the key of 0 and the value of foo into my array. What's really convenient is this one kind of works as a direct access map. What I am going to do to translate these is I am simply going to mod any key, which in this case so far I'm only dealing with ints, by the size of the table. And because I'm bad at math, I chose a table of size 10 to make our math easy. So 0 mod 10 is 0. So I put my value there. 5 mod 10 is 5. I put my value there. But now I have 11. That's outside of the range of my array. 11 mod 10, 1. So I put my value there. 18 mod 10, 8. I put my value there. I've translated a wider range of keys to a smaller range of possible indices. So I have now at least solved my wasteful space problem. Anybody forward thinking can see some problems? Yeah.
28.
28. What a perfect suggestion. According to the way I'm doing this, what index should something to 28 hash to? 8. But 8 is occupied. Problem. So I'm going to talk about that essentially for the next day and a half. But just so you can kind of look at some code, here is how we would code up that previous thing I was just talking about, as if we pretended that 28 never existed. And so you can see all I've done is instead of passing key directly between the square brackets, I now have a hash to valid index function that does this little mod step for us. And again, as long as we sort of pretend 28 never gets added, I keep my beautiful constant time lookup and placement. And that's the best I can do. Instant access to a dictionary, delightful. No matter how big the dictionary is, great. Yes, question? Because you could tell I had some wasted space there, and then what if I run out of space? Am I going to need to resize? Absolutely I am. In fact, anytime I use an array as underlying storage, the charming problem of running out of capacity and then doubling the space and then copying everything over will incur, and that is absolutely something that will happen to this too. But guess what? There's a bunch of really complicated ways to do that as well. Again, that's why I'm going to talk about this for a whole day and a half. So, the thing that I've been avoiding talking about, that problem that I've been pretending doesn't exist, it's something called a collision. So here is our problem from before. But what if I try to put 20, I guess is the example I picked here. Collision. Collision, by definition, is just when you have two values that hash to the same index of your underlying array. And it turns out there is a ton of different ways to decide how you are going to handle this situation. So, there are two things in trying to keep our design of the hash table as close as possible to the perfect constant time runtime. The two things are, one, what do I do when some type of collision happens? Because the collisions are actually kind of dictated by your data set. And we as programmers, we don't really have control, over the data set necessarily. We don't have control over what names people have that need to be stored in our collection. Maybe everyone has a bunch of similar names. Very common, right? But what do we do when there is inevitably a collision? But then also, two, how do we try to minimize the number of collisions that exist? And these are the two questions where we will be making a ton of design trade-offs. Sometimes you'll decide to just handle the collisions, just let more collisions happen because it's more expensive to avoid them, and vice versa. Okay, there's two basic categories of strategy for how to handle collisions. The first is called separate chaining. And I love it because it is just so beautifully simple. If two things collide, well then make that bucket bigger. Just let them both live where they want to live. So we're going to transform each index of the array into a collection. Welcome, we now have a data structure of data structures. I'm going to show you what that looks like. But then essentially, whenever you have a collision, just have something that can store multiple things there. The second category is if we have a collision, then we apply a second hash algorithm on top of it to try and find a different and possibly open location. So it's if that one's full, then go try to find somewhere that isn't full. We're going to start with the separate chaining solution, and then I will probably spend a lot more time talking about the open addressing one on Monday. Yeah, question in the back? Oh, this is interesting. Okay, when you have to because then it's like, how do I deterministically find my keys if they're going to be stored within a collection of a collection kind of thing? We're not going to change the keys in this particular case, but I would not be surprised if there exists some design just like that out there in the world. I'm going to show you how we do it, and it is straight up not as clever as what you just suggested. This is what a separate chaining looks like. It is most commonly used with a linked list. So what we do is we make an array of linked lists. So if that index has nothing that has hash to it, it's just null. That means that bucket is empty. I'm going to use the term bucket to mean the index of the array that can hold multiple elements. Or if we have some collisions, well, we just have a linked list and we just sort of make a new node and hang it off of the thing that got there first. So what happens is, in order to find the thing we're looking for, first we hash it to find which index of the array it exists at, and then we need to do some search through the linked list. So you can see here, we'll get constant time lookup of 22 and constant time lookup of 13, but to find 21 or 17, I would have to jump into index 1, and then I would have to loop and say, 1, are you the number I'm looking for? No. 21, are you the number I'm looking for? Yes. Now, just for context, I know I kind of went from showing you 2 values to 1 value. That's just straight up because I can't fit pairs on the slides, and I am almost always talking about keys in this context, because in the dictionary, it's like the value's kind of along for the ride, and we really just care about how we organize the keys, get access to the keys, change the keys, that sort of thing. So just visually, I'm just going to show you the keys. That's what we're talking about here. But yeah, you can see here's some pseudocode. The first thing we do is we find the bucket of where the thing is supposed to be. We loop through that bucket. We return true if we find it. Return false if we never find it. Yes?
So if we look at the runtime of this, would it be somewhere, if assuming that each linked list is about the same size based on our hash function, wouldn't it be something along the lines of f of n equals n over the size of our array? But wouldn't that still give us big O of n?
Okay. You literally pre-guessed 2 separate slides, which is incredible. So we're going to start with the first one. But you definitely just essentially talked about lambda, which is at the back of this. So excellent foresight. Okay, let me put this in a different way that maybe our brains can. Okay, so we're looking at this. Can anyone think, what is the worst case scenario for a separate chaining hash path? Think about it in terms of collisions. How many collisions in terms of n is going to give us the least efficient chaining hash map? Anybody, any brave souls? I heard some of y'all murmur it, and you were correct. How many collisions out of n is going to give us the absolute worst runtime? If my perfect runtime is constant, and my worst runtime was that array at the beginning where I had to just look at every single thing, and it gave me linear runtime, what's the worst case runtime, i.e. a linear runtime? Yeah. Infinite collisions or n collisions. Gross. What if every single thing we added to the hash table collided to the same bucket, and so we just ended up with a mostly empty hash table, but one singular linked list that we then have to loop through? That singular linked list has an n runtime. This sounds judgmental, but I swear it's the term of this. This is called a degenerate hash table. Vibes. We can't technically always prevent this, again, because we don't have full control over the data, but we are always trying to reduce the likelihood of this happening. Now, in this particular case, here's our code. You can see I now have 2 separate functions. One that says hash to valid index, and then the other one that's called get hash. Get hash is going to take whatever my key is and give me some number that represents that key. Then get it into the valid hash. That's the one that does the mod by table size. So what I did here is I have a bunch of keys, and apparently I forgot to change these. Ignore that, the A and Bs. Where I just picked a number to represent the string by the length of the string, so everything that was one length of string all hashes to the same thing. Not a good hash function. Okay, if this is the worst case scenario, what is the best case scenario? If the worst case scenario is infinite or n collisions, what is the best case scenario in terms of collisions? Zero collisions. Because zero collisions means that I don't have to do any looping over the linked list. I'm just going to find the one thing in that one box. So in this case, I did change the slide appropriately, and I decided to find my number by grabbing the first letter in the string and casting it to an int, and since the first letter in the string is all different, they all end up in a different box. Huzzah. But now it is going to be our job to figure out how to do this translation that's going to give us the most variance of that magical hash number to represent our keys so that we can reduce the number of collisions. So if the worst we can do in any hash table is O of n, the best we can do is O of 1, and our job is to try to keep us as close to the O of 1 as possible. And in fact, when you use hash tables with the stuff that I'm going to teach you over the next few days, you actually statistically do end up so much closer to the O of 1 that when you're in an interview and somebody asks you what's the runtime of a hash table, it is like the one time they actually do not mean worst case scenario because they expect you to say O of 1. Hash tables are expected to have an in-practice runtime of O of 1. That is why, again, in an interview scenario, if they ask you something and they're like, here's a bunch of data, do something with it, and you're like, I have no idea what you just said, just try to jam it into a hash table. It's kind of a joke, like when in doubt, hash it. That seems to be pretty good because it's hard to literally create any other structure where you get constant time lookup. It's truly incredible. It's the Beyonce of hash tables. All right. So there's a bunch of stuff in here then. This is about sort of that range between constant, but like I said here, people consider hash tables to have a constant time lookup. I'm going to show you all the things you need to do to keep it in that state, but in practice, yes. A hash table has constant time lookup, constant time put. Okay. This is something you are going to be implementing for your homework. You're going to be implementing the separate chaining hash table. So there's a bunch of stuff in here that you can read in a little bit more detail. But now I want to come back to my friend's suggestion about what happens when we need to resize and what's the runtime based on how long each of those chains are hanging off of the array. Okay, so because we now have a data structure that allows you to overload each of the buckets, we need to start thinking about the balance between the overall array capacity and how long any of these individual chains are. Lambda, or load factor, is an average numerical value to give us an idea of how full the hash table is. So we take the number of items stored across all buckets of the hash table, or the current value of n, divided by the capacity of the array. So lambda, which is this little Greek symbol, okay, lambda equals n over c. So here we have a capacity of 10. We have an array that goes from index 0 to 9, so it has a capacity of 10, 10 separate buckets, 10 separate linked lists. Stored within it, we have 1, 2, 3, 4, 5, 6, 7 items. So its lambda, or load factor, is 7 over 10, or 0.7. So when we're talking about the runtime, if you're talking to a academic computer scientist or a mathematician, technically the runtime is O of lambda. But every engineer finished their computer science degree and promptly forgot what the heck lambda is, and if you say O of lambda, they'll be like, I don't even know what is that? I was asleep that day in 373. So they will expect you to say O of constant, but what's important about lambda and important for your P2 is lambda is going to help us decide when it's time to resize the underlying hash table. Because technically, we have infinite capacity in this hash table as it lists right now, right? Like each of these linked list could go on forever. But if those lists get too long, well, then what the heck is the point of having a hash table? So the convention is to resize when you get to a lambda of 1. I think in your homework assignments, we let you actually decide what value of lambda to resize at, because this is a point of balance. If you resize too often, remember, resizing is expensive. And one of the things to think about, too, is because each of these locations in the hash table is dependent on the capacity of the array, right? Like that's how we know which index for it to get at. If we resize the array, then we have to go in and rehash everything because we need to find its new location. And this is something you're going to have to program in your P2, where when you hit a lambda of whatever you decide, let's say 1, then you make a new hash table of double the size, and for every single key stored inside of it, you have to put it back through your hash function and mod it by the new table size and then put it into a new location. That's a pretty expensive operation, so we don't want to do it too often, but we don't want those linked lists to get too long. And so again, it is about balance. Where do you find that optimal balance point between keeping the linked list short but not having too much wasted space and resizing too often? Questions so far? Yeah.
So for the resize, would we say like the worst case asymptotic runtime would be like O of n?
So yes, technically the worst case runtime of any hash table is O of n in the separate chaining model, and that's if we have that degenerate hash table where we've just got one linked list of size n. The in-practice runtime is really O of lambda, but most engineers will just say O of 1 because that's much more statistically likely. You have to almost like try to get n collisions or just write a really bad hash function. Other questions? Okay, you look less terrified than the analysis lectures, so I'm going to consider it a win. Okay, I've been saying this thing about hash function. I kind of showed you one on a crappy slide, but the hash function, that's that method that takes your key and translates it into a numerical value. So the first thing we could do is we could just come up with some type of numerical value to represent anything. And so like, let's say we have string keys, like in an actual English language dictionary. So maybe one number that represents a string is how long that string is, but that is not very deterministic. We're going to have a lot of collisions. There's a lot of words that have the same number of letters in them, right? Yeah, question?
Yeah, so when you were saying that we rehash everything, shouldn't your hash function be independent of the capacity of the data structure or the hash value?
So you want your hash function to be deterministic of the key so that you can constantly resize the underlying array to make that balance between wasted space and length of things. So that's why we keep the hash function separate from the mod by table size piece. Because the table size might change even within the state of the same. So maybe, okay, to get a more deterministic, fewer collisions number that represents a string, maybe we like include more aspects of the string. So this is a hash function that loops over each individual character of a string and then casts each character to its ASCII value. Like for example, lowercase a just is represented by the number 97 in the ASCII code, and your computer knows that. And so if you like put 2 parentheses around the word int in front of a character, it'll translate your like lowercase c to 97 or your lowercase b to 98, so on and so forth. So maybe we like cast all of our characters to ints and we sum it up. So in this case, now finally, like the words cat and dog would have a different hash function, whereas in implementation 1, they would both have the length of 3, so they would collide. Now we're actually taking letters into account. There's fewer collisions. But, you know, words like cat and tack, they would have the same hash function because they have the same letters. They're in different order. So we could even go deeper where we could, in fact, take into account the position of each letter, and also you'll find that prime numbers are super popular in hash tables. And in fact, one of the conventions is instead of using a hash table of size 10 that has a lot of divisors, make a hash table that is of size prime. So when you're modding by prime, there's even fewer collisions, things like that. This one is doing some crazy work where it like raises every letter to the different prime based on its location. So this is going to be super few collisions, but remember, you have to call the hash function not only when you get a new piece of information, you put it into the hash function, but you also need to call it anytime somebody gives you a key and you need to go find which bucket that thing lives at. You also need to call the hash function anytime you resize. So you want your hash function to be real fast because get hash tends to be the thing that's called the most often. So this is another point of balance. How can we come up with a hash function that will produce the most variance across our keys, but also execute really quickly because we have to call it super often? I'm going to leave it there for today. Come back on Monday. We're going to finish more about how to write a good hash function, and we're going to talk about open addressing. Thanks so much, everyone. Have a great weekend.